Okay, so moving on, I just did a recap on random variables, distributions, probability, etc. Now I will make a quick recap on statistical inference. Uh, I will make a quick overview on how statistical inference is called. That is called the null hypothesis statistical testing, or some people just know it as statistical inference or inferential statistics. That is also abbreviated as NHST. Okay, why is it called null hypothesis statistical testing? That's basically because it follows the Neyman-Pearson's lemma. So this is Neyman and this is Pearson. Uh, so this lemma is basically followed by all of us, that we need to specify our scientific hypothesis, normally expressed in verbal terms, in terms of null hypothesis and an alternative hypothesis. That is, they are called H0 and H1. H0 is going to specify that our parameter is equal for another thing, for example, a value 0 or something like that. And H1 is going to be the complementary to H0. The NHST specifies a framework that was inherited by the signal detection theory. That the signal detection theory just assumes that we can affirm that we hear a signal, or we do not are hearing a signal, we just hearing noise, but actually the signal can be happening or not. And there are four possibilities emerge. For example, if I say that I'm hearing a signal and there is a signal, it's a hit. If I say that I hear a signal and there wasn't signal, it's called a false positive. If I say that I don't hear any signal and there is a signal, it's a false negative. And if I say that I don't hear a signal and there is no signal, it's also called a miss, or a correct rejection. This framework is typical in the decision theory, for example, with tests in medical sciences, and we can apply it to statistical inference. So we can create a scenario when the H0 is true or false, and we can reject H0 or maintain H0. So there are two types of error, false positive and false negative, that are translated as type 1 error and type 2 error, and have an alpha and beta probabilities. So a false positive should be rejecting H0 that is true, that's a type 1 error, and maintaining an H0 that is false is also a type 2 error. Therefore, we can specify their complements. And then if I choose to maintain an H0 that is true, then that's going to be called confidence, and this one minus alpha. And also if I choose to reject an H0 that is false, that is going to be called statistical power, and this 1 minus beta. Okay, so the NHST assumes that our sample statistic is bound to sampling error. Therefore, we are not sure that it is giving us the right information about the parameter. And we don't know the sampling distribution of this statistic, for example, means, medians, modes, etc. And however, we can manipulate that information to obtain a test statistic that we actually know its sampling distribution. For example, a t statistic for a t test, the f statistic, etc. So we can create a density distribution to two scenarios that are basically when H0 is false and when H0 is true. You can see here, these are the two densities. And then we can create a limit or a criterion that will separate if we reject H0 or we accept or maintain H0. Therefore, if we commit an error, for example, that we are in this density function that is in the H0 being true and is in the rejection region, is going to be called type 1 error, alpha. The opposite region is going to be called type 2 error, beta, and therefore confidence and power are easily specified. Okay, so this is the practical example in the situation of being a judge and need to decide to condemn someone. So it's kind of intuitive. I will leave you guys up to it if you need to review this. Okay, so The thing is that NHST only works with the distribution, the sampling distribution that assume that H0 is true, with therefore only two zones that are concerned with, alpha and 1 minus alpha. Therefore, we can make two-tailed test or one-tailed test. Two-tailed test divide alpha by 2, and one-tailed test just puts all of the alpha in one of the sides of the distribution, and therefore we will specify a region of rejection that is going to be called alpha and has this amount of probability, and also the remaining region is going to be called the maintenance region or the acceptance region, and is going to be called quantified as 1 minus alpha. Okay, so in addition, alpha and beta are unknown, that we need to specify them. Therefore, this is the typical thing to do is to specify alpha as 5%, 1%, or 0.1%. Therefore, 1 minus alpha is specified as 95%, 99%, or 99.9%. This is a typical 3-star system. Okay, so then we can create a p-value. The p-value is the zone of probability of the sampling distribution that is associated with our test statistic. Therefore, it encapsulates the probability information of our data. Then we can test or compare the p-value towards our specified alpha, and if it's lower, we can reject H0 and we can say it's statistically significant or there is an evidence for an effect. If it's equal or larger, we can choose to maintain H0 and say that it's statistically not significant or there is no evidence. This is important. It's important to, if we maintain H0, therefore we affirm there is no effect. That's not true. Absence of evidence is not evidence of absence. So if P is lower than alpha, there is an evidence for an effect, but if P is equal or higher than alpha, there is no evidence of anything, of an effect or the absence of effects. We cannot affirm the absence of an effect with this technology. Okay, so if we complement this p-value with an effect size estimate, a parameter estimation with confidence intervals, we can say that that's okay. That's the current NHST. Okay, so now I would like to elaborate a little bit on p-values, because it was like an inconclusive debate between Fisher on one side and Neyman and Pearson on the other side. The scope of Fisher was basically falsationism, and it was based on a classical perspective that induction was done by inference. Therefore, only H0 is dealt with, and the NHST is just a technology that can tell you the likelihood of H0. Therefore, the p-value is a conditioned probability, is the probability of getting your data, assuming that H0 is true. There is no room for accepting or maintaining H0, so there are only two ways: rejecting H0 or the experiment is inconclusive. H1, there's no need to specify it, therefore power is not considered, maybe some sensibility of the experiment, and type 1 and 2 errors are meaningless. We only need the p-value. However, Neyman and Pearson had a broader perspective that was more behavioralist, if you can say, that assume that H1 is necessary and needs to be specified, and therefore power and type 2 error is also specified, and H1 is competing against H0, and therefore type 1 and 2 errors hold some meaning. And finally, p-value is a more abstract description or a manifestation of alpha based on our data. Therefore, confidence and powers must be quantified. This was inconclusive, and there are some references over there if you want to get more in detail what was going on and what was the debate about. The current NHST is a mix of these both postures with a lot of common careless practice and scarce understanding of what was going on. In addition, we have the limitation that H0 is unknowable by NHST. So if you want to do a good NHST, you need to specify your broad hypothesis, specify your alpha with some arguments on why are you doing that, claim a decision on your p-value, make a power analysis to specify your power and justify that your sample is enough, and also complement with effect sizes and confidence intervals. Okay, so now I would like to talk about the criterion of alpha being 0.05. It could be intuitive, but actually it was a dichotomization and also rounded by Fisher. It was aimed to avoid a copyright dispute with Pearson, and it was basically convenient, as Fisher put it. 95%, 1 out of 20, because there were other prospects, for example, 2%, 1%, etc. Fisher, from the birth of this criterion, was saying that it was never meant to be used as a fixed criterion or in just one experiment. However, software like SPSS and other alternatives massified this criterion into the 3-star system. That is the typical 5%, 1%, or 0.01%. Okay, so there were other alternatives. For example, Gousset's proposed 0.02. So this is like a quick recap on statistical inference from a frequentist approach. So now we will move on into the current state of affairs.